All right, let's just jump right in. For years, we've all been taught to think of SHA-256 as this impenetrable black box, right? A one-way street for our data. You put something in, and it's gone forever. But what if that's just not true? What if the whole idea is wrong? In this explainer, we're going to look at a totally different way of seeing one of the world's most trusted algorithms. We're not talking about a random paper shredder anymore. We're talking about a machine that can be understood and maybe, just maybe, run in reverse.
So the story we're always told about SHA-256 is that it's all about creating chaos. You feed it a message, and this thing called the avalanche effect kicks in, spitting out a hash that's just completely scrambled and unpredictable. The idea is that your original information is just destroyed, gone. And this whole concept, it's called the random oracle model, and it's pretty much the bedrock of modern crypto.
But what if that's all just a big mathematical magic trick? A new way of looking at this says, forget the chaotic shredder. Think of SHA-256 more like a deterministic machine, a geometric projector even. It's not actually destroying information. No, it's folding it. Kind of like cryptographic origami, you know? It's just folding your data into a really specific, predictable shape based on a very strict set of rules.
And that brings up a pretty big question, doesn't it? If it's really just a machine, like some kind of clockwork engine just following a set of instructions, then why can't we just run it backward? I mean, what's really stopping us from taking a hash and just unfolding that origami right back to the original message? Well, that's the big mystery we're going to unpack right here.
Okay, so if we're going to figure out how to reverse this thing, we've got to pop the hood and see how it's actually built. See, the architecture of SHA-256 is based on just a few really simple operations, but the magic and the headache is all in how they're mixed together.
Right? So SHA-256 belongs to this family of algorithms called ARX ciphers. And that name, ARX, it's basically just an acronym for its three main moves: modular addition, bitwise rotation, and XOR. Now, by themselves, each of these is super simple, really fast. The genius, and the big problem for us, is how SHA-256 braids them all together.
And this is where things get really interesting. You're looking at the core conflict right here. SHA-256 deliberately weaves together two totally different mathematical universes. On one side, you've got the world of XOR. It's clean, it's linear, it operates in something called Galois field 2. Think of it as simple addition, but with no messy carry bits to worry about. Super easy to track. But then, on the other side, you've got regular modular addition. And that's where the chaos comes in. It creates this cascade of carry bits that creates all the complexity and nonlinearity. And the algorithm just smashes these two different realities together.
And this braiding, this mixing of two totally different kinds of math, one linear, one nonlinear, this is exactly what builds this giant, insurmountable wall. It's what stops anyone trying to reverse the algorithm with the usual mathematical tools dead in their tracks.
So the standard way people try to crack this is with something called a grinder attack. It's pretty much what it sounds like. You get a really powerful algebraic solver. Think something like Newton's method from your math class, and you just aim it at the hash and hope it can grind its way back to the answer. The problem is, it's basically guaranteed to fail, every single time.
And here's why. The solver runs smack into a mathematical brick wall. It's called a two-adic singularity. Basically, in the base 2 math that all computers use, that whole braiding of XOR and addition, it forces key values in the equations to always be even numbers. Now, in the kind of math we're dealing with here, an even number just doesn't have a modular inverse. Trying to find one is literally like trying to divide by 0. The math just breaks. The solver crashes. End of story. It's an absolute wall.
So, if the abstract math is a dead end, a total brick wall, what do? Well, the breakthrough is to stop looking at the math altogether and start looking at the machine. The secret isn't buried in the equations, it's etched in the silicon.
And this is the big pivot in thinking. The math just isn't working. So, you change your perspective. You stop looking at the algorithm as an abstract piece of software, and you start looking at the physical hardware, the actual logic gates on an ASIC chip that are doing the work. And when you do that, you find something amazing. That addition operation, it's not what we thought it was at all. In the real world, on the chip, it's done with something called a carry-save adder.
So let's dig into that, because looking at the hardware completely changes the game. This jump from software to silicon is what finally lets us unbraid those two worlds that SHA-256 tangled together.
Okay, this right here, this is the big aha moment. It turns out that in the actual hardware, modular addition isn't one single thing. The carry save adder, what it does is it physically breaks that addition down into two separate parallel streams. You get one stream that's just a simple, pure XOR sum, and a completely separate calculation for all those messy carry bits. They get calculated, shifted, and then added back in. So that whole braiding we were talking about, it was just an illusion created by the software. Down on the chip itself, the threads were separate all along.
So just like that, the physics are unbraided. We now have two completely distinct channels. First, you've got the linear path. This is a perfect, clean stream of pure XOR logic. No carries, no complexity, and, this is the big one, no two-adic singularity. It's gone. Then you have the second channel, the nonlinear correction. This is where all those messy carry bits that kept crashing our solver have been shoved off to the side. They're isolated into this predictable, thermodynamic exhaust. We've literally found a way to walk right around the wall.
And get this, look at the data here. This so-called chaotic part, the nonlinear correction that seemed so impossible to deal with, well, it turns out it's actually tiny and really structured. Out of 32 bits, the Hamming weight, which is just a fancy way of saying the number of active on bits, is only about 5 to 9 bits each round. That's not chaos. It's a tiny, predictable, measurable signal. All right, so now we've got this clean, perfectly linear channel completely isolated. The big question is, what can we do with it? Because this is where the road to actually reversing this thing really starts to open up.
Because it's a purely linear system, we can finally bring out the big guns of linear algebra. We can build what's called a Jacobian matrix to describe exactly what the system is doing. But when we do that, something totally unexpected happens. Something that, at first, looks like a huge problem, a really stunning mathematical anomaly.
So when we analyze the linear system over 6 rounds, we expect to get a matrix with a rank of 192. But it's not. The rank we get is only 156. That means the system isn't firing on all cylinders. It's got this massive 36-dimensional blind spot. It just can't see everything.
This is what's known as a rank deficit. And what it means is that there are 36 whole dimensions of information, 36 different directions that data can move in, that the linear part of the SHA-256 machine is completely, totally blind to. It can't see them, it can't touch them, it can't interact with them at all. And this thing that looks like a major flaw, it's actually the key to everything.
And here's the final twist in our thinking. That 36-dimensional blind spot, it's not a bug, it's a feature. In fact, it's the ultimate free filter.
So here's how it works, and this is so clever. Because the machine is blind to these 36 dimensions, it actually imposes 36 really strict geometric rules on any possible answer. You can think of them like the laws of physics for the system. Any potential solution you want to test has to obey these laws. If it violates even one of these simple rules, like a parity check, you know instantly that it's a geometric impossibility. You can just throw it away, with zero computational cost. This lets you just obliterate huge chunks of the search space for free.
And the final step is just elegant. You take the linear solution that you found using this awesome free filter, and you treat it like a perfect skeleton, a scaffold. Then you do this thing called a proper Hensel lift, which is a fancy way of saying you carefully add back in that tiny predictable carry correction that we set aside way back at the beginning. This process lifts your clean, simple answer from the linear world right back into the complex, full SHA-256 world. And just like that, the reversal is complete.
So this whole journey just completely flips our understanding on its head. SA-256, it turns out, isn't some random paper shredder after all. It's more like a piece of deterministic clockwork, a precise geometric mold. And if that's true for one of the absolute cornerstones of our digital security, well, it really makes you wonder, doesn't it? It forces us to ask a much bigger question. What other fundamental ideas about how all this stuff works have we gotten completely wrong?